Thanks very much. So, as Abasi said, this is based sort of roughly on a TED talk that I gave in Sydney a few months ago. But TED Talks are hugely sort of popular level talks, and this one I wanted to go into a little bit more technical detail on some of the things. Some of the things here are slightly overlapping with what you might have heard at the conference the other week if you were there. But basically what I want to talk about is not so much the science of quantum computing and quantum networking, but what the implications of that are. Everybody's focused on how to build things and how to go about constructing things. Very few people are talking about, well, what does this mean in terms of how does humanity progress? And so I started thinking about these sorts of things when I was working with the Chinese. As you know, Jian Weipan, very well-known Chinese scientist, put up this amazing quantum satellite not long ago. And all it does is one thing, is it spits out these bell pairs, entangled pairs of photons at a very fast rate. Fast enough that at base stations almost 2,000 kilometres apart they can receive these bell pairs, and they use this to do provably secure quantum communication using quantum key distribution. But there are lots of other things that this sort of technology will lead to beyond just quantum key distribution, and those are the things that actually have the biggest potential implications, I think, politically and strategically, which is what I want to have a look at. So just in case the audience is diverse, there's very little mathematics I'm going to use. The first notion is just a qubit, which is a superposition of 0 and 1, like a bit, but in superposition. We use that first line of the notation. And the only other notation I'm really going to use is the bell pair, which is just a maximally entangled state of 0, 0 and 1, 1, or something similar. And in photonic encoding, like what they did in this satellite, they just map these 0 and 1 values to polarization degrees of freedoms in the photons. You have a single photon, and if it's horizontally polarized, that means it's 0, and if it's vertically polarized, that means it's a 1, and that's how they encode a qubit into that. So the first thing that you can do with that is quantum key distribution, and the first ever quantum key distribution protocol that was come up with was called BB84, named after the authors, and the way it works is what you do is from Alice to Bob, these are the two people that are trying to securely communicate with each other. Their initial goal is just to share a long random bit string of random bits, nothing else, no message at this stage. And so all they do is Alice just randomly chooses between one of two bases, the horizontal vertical or diagonal and anti-diagonal. And then she randomly chooses a bit, either 0 and 1, which is mapped accordingly to whichever basis she chose, to one of the two states in that basis. She randomly chooses bases, she randomly chooses bits, and she just spits them out over and over again to Bob. And he randomly measures in bases, either the horizontal, vertical, or diagonal, anti-diagonal bases. And then at the end of all of that, they just publicly, on an open channel, it doesn't have to be secure, they just say, oh, okay, Alice says, I transmitted in this combination of bases, but without revealing what the actual bits were, just the bases. And then whenever Bob realizes that he agreed and he'd measured in the same bases, he knows that he must have got a consistent measurement of the bit that was sent, and then they have one shared random bit between them. If they had disagreed and Alice had sent in one basis and Bob had measured in the other basis, then it would be completely randomized garbage and they just throw it all away. So they end up losing half the bits, but what's left over is a long random bit string. Why do you want that? Because now you can use this as a private key for what's called the one-time pad protocol, which is the only provably secure cryptographic protocol whereby you need a bit string as long as your message. You do an exclusive OR, bitwise exclusive OR operation between the two, and what's left has maximum entropy, and you can extract nothing from it. The trouble is it's called the one-time pad because you can only use the key once. And so this is why it's not a very practical encryption scheme to use, because, well, if you want to send a message to your friend over the internet, you don't want to have to go and meet them in advance every single time to give a new key. You want to be able to keep reusing keys. So what this quantum key distribution protocol does is allows us to overcome that problem by having a constant ongoing stream of shared randomness between the two parties. So another way to do that is using entanglement. It's almost identical in the way it works. What we do is we have our satellite up the top, the one that I just showed you. It spits out these... Sorry?
You're getting the feedback.
So, oh, okay.
So either we switch off this.
Yep, sure.
And you're using a mic or?
No, I can just yell.
Oh no, don't yet. Just
Okay.
this. So this is volume. This is a volume.
Okay, is that better?
Yeah.
Okay, great. So in this other one, the entanglement-based one, you have the server, which is the satellite or whatever that's sharing the entanglement, and you have the two parties with this maximally entangled state. And now what they do is they both randomly just measure in different bases. Again, either horizontal, vertical, or diagonal, anti-diagonal. And in the instances where they've measured in the same bases, they must, by that correlation, get consistent answers. In the instances where they haven't measured in the same bases, they'll necessarily get randomized garbage, and then it's the same protocol as before. They just throw that away, sift it away, and what's left over is a shared random string. So that latter approach is the one that you can use from, for example, a satellite that's acting as an entanglement server. You can do other things, though. Notably, suppose you've got a qubit, a quantum state, that you want to directly transport from one person to another. Because of the no cloning theorem, we know that we can't keep manufacturing copies of important quantum data if we don't know what it is. So if we lose it over a lossy channel, for example, or the channel isn't very good quality, then it's gone, and we've completely lost very valuable information. So an alternate approach is to use state teleportation, whereby you take an entangled pair and your original qubit, you send the entangled pair between the two parties that want to communicate with one another, and then the first party does a joint Bell measurement on their qubit with one half of the Bell pair, communicates just a classical measurement result to the other party, and then magically that qubit appears at the other end. But it bypasses the quantum channel entirely. The qubit that you're starting with at the top doesn't actually pass through whatever quantum channel is connecting those two people. The quantum channel is only used to communicate the entangled pair itself. So why is that advantageous? Well, entangled pairs are infinitely reproducible because it's a known quantum state. You don't have to worry about this no cloning limitation. You can make as many of them as you want, and if sometimes it fails, doesn't matter, you try it again. And so you can overcome channel limitations that way. But then it gets even more interesting because unlike classical networks and classical computers, different laws of physics imply different laws of what we can do with the laws of physics. And so when it comes to a quantum network, the two things that we can do that we can't do classically are entanglement swapping and entanglement purification. Entanglement swapping means that multiple links that have entangled pairs, they get to join them up and magically end up with a long-range entanglement link between parties that had never touched each other. And entanglement purification means you take multiple copies of Bell pairs and reduce noisy ones down to a smaller number that have much higher quality. Now, if you combine that with the notion of state teleportation, it means that now we can communicate qubits with less noise than what would in principle be allowed by a direct use of the channel itself. If the channel has a particular noise threshold applied to it, we can overcome that and do better by purifying the entangled states that we're using to teleport with. Another notion is the fact that we don't need to worry about latency with state teleportation because entangled pairs are all identical. They don't contain the information itself. And so it doesn't matter how slow it is. You could put it in the back of a truck and transport one half of an entangled pair between two people. And as long as it's still a Bell pair at the other end, you can just use it on demand. And so we don't have latency issues the way we do in normal classical networks. So that's all been talking about communication, really. What about computation? That's where it gets really interesting. Well, if we take a network with two classical computers and put them side by side, whether they're connected or not, what you're left with is cumulatively twice as much computational power. It's just additive. All the communication does between them is allow them to share information, but it doesn't give them any kind of enhancement in their actual computational power. When it comes to quantum computers, that's not the case because we know that there's a nonlinear relationship between the computational power of a quantum computer versus the number of constituent qubits or subunits or CPUs, whatever you want to call them, in that quantum computer. So if we have multiple quantum computers and they're acting in isolation, their collective computational power is additive, just the way it is for classical computers. But if we network them in such a way that they behave as one, then the joint power is far greater than the sum of the parts. And now that's really important because it means that we immediately see that there's a strong incentivization to start networking the world's quantum computers. At the moment, as you all know, we have this Moore's law trajectory that we've been following ever since computers began, but that's beginning to flatten off. We can't really go much further with classical computers than we currently can because we just can't make transistors that much smaller than they are. So Moore's law won't last forever, and quantum computing allows us to overcome this by using quantum bits instead of classical bits and provide algorithms where the scaling relationship is improved and we get much better return on the number of constituent physical units. So to explain this, I'm going to look at the measurement-based model for quantum computing. This is what's called a cluster state. The nodes represent qubits prepared in the diagonal states or superposition of 0 and 1. And the links, the edges between them, represent the application of controlled phase gates. And once you have a substrate of a lattice like this, you just measure out qubits in particular choice of bases, and some smaller number of qubits are left at the end, which encodes the answer to a computation. You can implement any quantum computation using that technique. What that immediately implies is that we have some now idea for what might be a really economical way to go about building large quantum computers. It's probably not a good idea just to build one big massive room-sized thing that costs a huge amount of money and there's very little demand for it. Now it makes a lot more sense to build modularized units whereby we can use these quantum interconnects, these little links, and they could be these bell pair distribution links or satellites, whatever the case may be. Each of these modules contains a relatively small size cluster state if we're working in that formalism, but it translates to other formalisms as well. And now we can patchwork them together using this lattice via these communications links. Now, what's the advantage of doing that? Well, the advantage of doing that now is that we have something that we can highly, massively reproduce, something that's modularized and you can mass produce it and get very, very good economies of scale out of it, as opposed to building enormous devices for which on their own they're so expensive that there'll be very little demand for them. If we can make these cheap and highly reproducible, even if internally it's just a very, very small cluster state, we have something that we can pump out on a production line very, very cheaply. And because these quantum links are just entanglement pairs and they don't have these latency issues, what that means is that this doesn't even have to be geographically centralized. It can be distributed. These units could be in universities and data centers all over the world, and nonetheless, via a potential future quantum network, they can be interlinked and all collectively act as one via this patchwork kind of idea. So what that means is that we now have a notion of cloud quantum computing, where we envisage a world whereby things are modularized, they're distributed, they're interconnected to collectively act as one. So we have this big distributed quantum computer. It's too expensive to buy outright. So what's realistically going to happen is that we'll unify the resources, and then the way that we do for any of you who use supercomputers, you buy timeshares in it. You write to the university administrator and say, I need to use the supercomputer for an hour. But now we're going to be doing it in the context of a market economy, where it's a globalized network of everybody's resources acting in unison, providing collectively far more computational power than any of the individual parts or what people could do on their own. After collectivizing it, they just securitize timeshares and trade them on the market. And so you can imagine that a market will emerge for timeshare use in this completely unified quantum infrastructure that could be within a country or across the entire globe. So now we have an immediate basis for commercializing this type of technology. But you can immediately see that there's a problem here. When you write to your university administrator to do some important work, you know that that supercomputer is one that's probably on campus and you can probably trust that they're not going to steal your PhD results. But if this is some big distributed device, well, surely you wouldn't want to do something sensitive, some commercial trade secret or something, knowing that maybe a large part of the computation is being done offshore or by someone you don't know where in this globally unified way. Thankfully, in the quantum case, there is a way to overcome this that does not exist in the classical case. And it's called, there are two very similar notions. One is called homomorphic encryption, and the other one is called blind quantum computing. And what this means is that a client that's accessing the global quantum cloud, they're able to prepare data that they want processed on this quantum computer. They can outsource it to the cloud or to any individual quantum computer. The quantum computer can process it in encrypted form without decrypting it first, return it back. The user, the client, then decrypts it to get their data. And despite the fact that it was outsourced fully to an untrusted cloud, potentially in another country that's adversarial, nonetheless you can have absolute integrity that the data wasn't stolen either during or before or after the computation. And that's a very important distinction. There is really no such parallel. In fact, it provably doesn't exist in the classical context. If you outsource to a supercomputer, you have to trust it. So now we have all the bits and pieces that we need for what I'll call the global virtual quantum computer, where we can see that there's a strong incentivization to immediately unify all the world's quantum resources. There's an obvious commercial model here because it can be done in a trusted way whereby you know that even though it's distributed across the globe, nobody's going to be able to, even in principle, steal all your data. Then we can create a common market for this, securitize timeshares in it, and that has all sorts of benefits. It means infrastructure can be decentralized the way current data centers already kind of do. The ad hoc nature of it means people can buy more modules and plug them in and just start collectively growing the collective power of this distributed quantum computer, the way that the current internet works with people just, you buy a new phone and plug it in and it works. It works in an ad hoc way. That's the benefit of having this modularized approach over a network as opposed to one big bulk homogeneous device. The other advantage is that if we were to securitize these timeshares and trade them on a market, it means that there's an immediate market incentive to ensure that this computational power is used in the most economically efficient way. And that is a huge driving force for investment. It also means that the market indicators on these investments, especially forward derivatives on what these contracts are valued at, that gives a direct market insight into what the driving force behind the technology is, what the expected future returns are, how we should invest in it. And this benefits all the market participants and incentivizes good resource allocation. So you can see now that compared to a conventional computing scenario, where the question is, do we cooperate or do we compete? We have very, very different circumstances indeed. If you had the current scenario where it's Alibaba on one side and Google on the other, and all of a sudden these two countries decide to go to war, the obvious thing to do is to start striking one another's data centers, taking out one another's infrastructure. That's the conflict scenario, and in the classical case, that's the obvious thing to do. But what if these are networked quantum computers now? They're on in completely different countries, but nonetheless they're networked in such a way that they're providing this exponential piggybacking off one another so that they're both mutually benefiting enormously from one another's participation in the network. Now you have a situation whereby if you undermine your opponent, you undermine yourself. If you take out the adversary's computational infrastructure, you immediately exponentially undermine your own computational capacity. And so we can immediately see that this is going to be, at least at the first order of depth of analysis, a strong driving force for cooperation and incentivization for not going around and adversarially undermining one another's capabilities, but rather trying to collectively enhance it because it mutually benefits everyone. Game theorists, of course, like to think about things as decision trees, whereby political decision makers, they look ahead and say, well, what happens if this happens and then that happens, and this happens and that happens? And the first order analysis that I've just provided is very simplistic. I've essentially just presented it at the level of, well, if we cooperate, then everything's fantastic, and if we compete, then we all self-destruct. But it's actually far more complicated as we start looking further into the tree. imagine this hypothetical scenario, which is completely believable. And that is using adversaries' quantum computers to gain competitive advantage against them without them even knowing by virtue of the fact that it's encrypted. So what happens is some guy in a bedroom in Russia with no access to quantum technology outsources a factoring algorithm that he can use to crack codes with. It's homomorphically encrypted, so nobody even knows that he's doing it. The computation is physically executed, potentially back in the United States, and then the guy in Russia uses it to hack into the United States. Okay, so you can see that that's a sort of game theoretic dynamic that's completely plausible in the environment that I described, and it's also one that's very undesirable. So as you start looking ahead, actually there might be reasons for it not to be as cooperative as we initially thought. There actually are some deeper reasons why, at a geostrategic level, this global network might start fracturing along geostrategic lines. Alliances might start forming whereby, the Five Eyes Alliance, Australia, United States, Canada, those countries, they trust one another in terms of intelligence and this kind of thing. And so they'll have their own little sub-version of this connected network. And then the adversaries, well, under no circumstances do you want them to get over the threshold whereby they can crack our own codes. So we'll just make sure that they stay below that, which means that we might invite them to participate in our network up until the point where they reach that threshold and then exclude them again. But you can see that this is getting very complex now. And so the whole game theoretic dynamics are being completely transformed. If you think of this as a payoff matrix in game theory, some of the amplitudes are now being massively distorted compared to what they are in conventional geopolitical considerations. It also has massive implications for Twitter. This is a predictable debacle that would happen. The fake news thinks the Russians are using our quantum internet, the best quantum internet, against us. I would never allow this. Sad. But of course, that's exactly what could realistically happen. So, in summary of the politics of that, of the geostrategic implications, we see that unifying our resources, it necessarily implies that every single individual who participates benefits both themselves and everybody else from a computational perspective. However, when you transfer what computations are used for, then it starts getting more complicated, and people might be willing to sacrifice even some of their own computational power by excluding others. And so this starts transforming the decision-making. It may not be perfectly cooperative after all. For example, large players could use a huge asymmetry. If you had a big nation state that had a huge amount of this quantum infrastructure on its soil, and then a small nation state approaching saying, hey, we want to network in and be part of this virtual joint quantum computer, and it'll benefit both of us, so why not? Well, the big state could say, don't care, give us something first, or alternately say, well, you're part of the network, we want something from you, otherwise we're going to cut you off. And this is unlike classical computing. You don't have the ability to do this. If I switch my phone off, I can't possibly destroy yours. But that's exactly now the situation that this is, whereby I can choose to have a little bit less computational power myself and completely eradicate yours if you're much more of a small player than I am. And so this could certainly be leveraged in asymmetric ways, and certainly you might imagine that this could be the equivalent of cannonboat diplomacy of the future, where this kind of technology is so essential to economic growth and development. So this is a little graphic from for our upcoming book that I drew that sort of captures the flavour of how this whole thing works. We have all of these different nodes that will potentially on different nation states, highly geographically delocalized. On their own, they wouldn't have very much, but now they can start networking using fiber links or these satellites that do entanglement distribution, or even ships sending bell pairs at a very, very slow rate, but who cares as long as they're well error protected. Then you have an international market for allocating the usage of those resources by selling them on as some kind of financial derivative or security, something like that. And at the same time, everybody can be surrounded by their own little insulated level of encryption, whereby they know that even when they outsource their computations in this way, everything is going to be fine from their perspective. So what we see is that Quantum technology is a race, but it's one that we don't want to become an arms race. It's one that we very much want to be a cooperative one. And it's an unparalleled opportunity for a symbiotic international interdependence that will be very, very difficult to break. So long as, for example, particularly amongst the major international players, so long as they retain relative parity, then there's no huge asymmetry, and the notion that if I undermine you, I'll undermine yourself remains valid. It's similar to sort of the mutually assured destruction concept. But if a huge asymmetry is allowed to emerge and some states end up becoming client states as opposed to relatively equal providers, that's when they're going to be enormously vulnerable to a type of diplomatic leverage that never existed in the past. We specifically don't want that to happen, and so we have a responsibility to try and make it that way. How do we do that? Using things like interoperable open standards, making sure that things are modularized and that in such a way that, just like on the internet, things interoperate and it doesn't just fracture into completely different national networks of any sort. But far more importantly, none of us can afford to abandon the principles that lead to that kind of openness and that kind of advancement, which is what led to the development of the internet in the first place. So how do we become a scientific superpower in that sort of sense? Well, the first thing is you need stability and reliability in investments. Just like in any investment climate, as a business operator will tell you, you can only retain retain economic capital, monetary capital, if there's predictable volatility in the markets. Science is the same. A major scientific superpower like this is at risk of losing scientists if there is no predictability in the scientific funding, and if it's volatile and the political circumstances make it uncertain. And so it's important that that doesn't get rejected. Major countries like this have the intellectual capital, have the labour force, have the infrastructure. My country, Australia, will inevitably be a client state. We don't have that kind of capacity. India certainly does have that capacity. The question is whether it has the political leadership to make it and to direct it in that sort of direction. Certainly the United States is already beginning to lose its scientific leadership status for the reasons that I've discussed on this slide. The rejection of rationalism and the embracement of what is not, in their case, ultranationalism. We don't want other major world powers to go down the same route. And in the Indian context, certainly much of this can be addressed in a far more eloquently expressed way than I can, and that is by this very fine document here. This very much captures all that's necessary for India to be guided in exactly the direction that is necessary to be a part of what I described, rather than an outlier and becoming a client state as opposed to a contributor. But as like any constitution like this, it's merely a piece of paper. It doesn't enforce itself. It's the same as applies in the United States. Instead, it's there as a basis to provide leaders to account, and so it's up to the people to do so. But right across the globe, certainly in the democratic world, we're failing to do so. We say at the beginning of all of these constitutions, we the people, but we fail to uphold it. It's certainly a ubiquitous phenomenon, and certainly in the United States, the Constitution has been completely trashed in favour of ultranationalism and polarisation, and for that reason they're losing their scientific status. We have to remember that governments can come and go, but scientific capital, intellectual capital, once it's gone, it's very hard to bring back. And a constitution even more so. Once that's gone, it never comes back. Why do I raise these sorts of things in an academic talk? It might seem a bit contentious. The reason is that all of these polarizations and rejections of rationalism that we're seeing across the globe, particularly amongst the major world powers, are things that are very much well recognised by the leaders, and that is that the greatest threat to an anti-rationalist campaign is rationalists. That's people like us. And the greatest threat to those who rewrite history is those who understand it. And that's exactly why there are efforts to try and silence us, and why that must be opposed at all costs. Certainly this happened only one generation ago. It happened in my parents' generation, when my grandparents were victims of this. There's this very famous poem written after the wake of the Holocaust. And you look at it and it makes perfect sense. And it's repeated in Holocaust museums all around the world. the question is that we can very clearly see the warning signs happening all around the world, all over again, and yet everybody is failing to take action. But it's precisely that phenomena that's going to prevent any of the things that I've discussed in the first scientific part of this talk from actually taking place, and it has to be overcome. That poem was written in relation to the cowardice of German intellectuals. Well, we're all intellectuals here, so let us not be the cowards. Richard Feynman very famously said, if you think you understand quantum physics, you don't understand quantum physics. I would rather say to most people of the free world, if you think you understand history, you don't understand history. And for that reason, people should study history, because otherwise, all of the things I've said in the first half of the talk are not science, but science fiction. Thank you.
Intelligence directors must be absolutely rolling in their sleep about this, but it's an unstoppable force. You can't stop this. It's not going to be exclusively caused by intelligence agencies. It would be completely ludicrous to try and prevent that. And the economic cost, the cost of not allowing this into the private sector would be so astronomical that it would be effectively playing Russian roulette for any nation state to do that.
Like any other resources, like oil, right? So powerful nations try to have a monopoly over these resources, so that nobody else even has it. So
that's right.
This case may happen with quantum which they say that we will have small nations in the nation, as you said. So that I can actually threaten this and say that I will cut you off. So so countries like the US, and maybe Russia, and even China, they might want to have most of the quantum network from their soil, so that they can control and actually threaten people.
Oh yes, they'll want to have as much of it on their own soil as possible, so that they have the ability, the jurisdictional ability, to decide who to cut off. Otherwise, they don't have the diplomatic leverage, right? That's precisely why I advocated before that it's essential that people try and maintain parity. We shouldn't allow certain big nations like this, shouldn't allow themselves to become just client states. They need to be equal players in a global playing field, so that this diplomatic asymmetry cannot be applied. Otherwise, everything you say is correct. But there's no reason why it has to be like oil, which is inherently an irreproducible resource, which just happens to lie in some places of the world and not others. Here we're talking about something whereby, once it's commercialized, you can mass manufacture it, anyone can buy it. And as long as a relative level of parity is maintained, then this diplomatic asymmetry will be subverted.
Yeah. So I understand that the comparison with oil was an diplomatic.
Sure, they'll still try and keep it that way. Artificially, you're absolutely right. But it's something that people can fight against by just building more in their own territory.
So, the way I would expect such a thing, if this is going to come to pass, how I would expect it to evolve is that once again, nation states will have enough quantum computational resource for their own strategic requirements, generate a strategic advantage, then by and large what we need to do is to solve the problem and put in place structures. So it's not that every computer you add to the node is actually required.
Oh, it may not get fully utilized. That's right.
There may be still a good size network which may be adequate, in which case there will be people who will be running these isolated networks which countries may afford.
Yep, that's right.
And they may have a quantum internet or whatever it is.
That's exactly right. Yeah, and if we go back to this cluster state, this sort of largest graph sort of model, that kind of fits very naturally, like what you're saying. Imagine now that you have a whole bunch of users competing on the marketplace. None of them could possibly need to solve an algorithm that's big enough that it requires the whole world cluster state of this. Well, that's very easy. Cluster states can be partitioned. Just chop them up and get around some qubits. They're partitions into smaller subclasses that can be used independently, completely independently. That's absolutely true. And that would just feed into another part of this securitization market. We're competing not just for timeshares, but for, say, a region of a lattice topology. Nonetheless, you can immediately see that there's economic advantage to keep contributing to it.
So, to play devil's advocate for your argument, I mean, the fact that one has had the capacity to totally annihilate the planet for like 75 years. That, and the fact that it has not yet happened, though there have been extenuating circumstances in this period, it kind of, there is a tendency not to wield, for humans, not to wield authority beyond a certain point. I mean, it seems to show, because the people who invested themselves in inventing the bomb, I mean, they were very depressed once they saw what was the destruction it wrought. So they went into collective depression. Now the point is that though people have been crazy and the world has had crazy leaders and they have been sitting on arsenals, they have not yet bombed each other, and there has not been a single instance of a nuclear kind of yes. So which means that there are certain in the human psyche there are certain limiting points. Of course, bad things have happened. We refer to the Holocaust. We refer to. I mean, you can always argue if there were another Hitler, would the guy have used stuff and blah blah blah. But
I'll tell you what I think is the answer to this. It's maybe based on redirecting the analogy. The concept of mutually short destruction, nuclear weapons, that's one that's purely adversarial. You trigger a bomb, you gain nothing other than to completely destroy the other person. And it's just a game theoretic standoff whereby both people have that. And they know that there's a guarantee that the other person's going to retaliate. It just sort of ensures the peace. But it's purely adversarial technology. This I would equate more analogously to the expansion of the internet across the computer system, whereby, yes, there are adversarial uses, but for the larger part, it's been the biggest driving force for human development that's ever existed. That's the difference. This is productive technology, whereas nuclear bombs are purely destructive technology. So from a game theoretic perspective, the whole thing is completely vertical.
yeah, but I mean, what I'm saying is that the malicious to sort of really, go out and say that malicious use of this can be catastrophic is not necessarily borne out by the historical
Malicious is very also used to make the other person comply. You will not annihilate that person. I mean, it's just that, I am threatening you is also something that can be used in
but that is anyway used
but then,
in
now
general.
this is a different
that's
technology that we're talking about.
yeah.
It's not about annihilation of the entire human race. And also you're putting too much credence to human beings and ability to destroy the world.
just the emergent property is that we have this fantastical network. We have the entirety of human knowledge on a device in your pocket. So it's a sort of an emergent phenomenon. I see this is very simple. If we have these modularized components, as I described, well, it's just a big self-interest part. And it's in their self-interest to unify, if possible, unless there's a really obvious strategic reason to not to. But as long as it's a highly competitive market and it's not monopolized, then a million minor players behave strategically very different to two major monopoly players fighting against each other, which is why it's important that we allow to go into the private sector. If you and I are allowed to have a module in our basement that's connected to the future quantum network, then the whole thing's unstoppable and it operates on the same brain principles that the internet did, which is the only reason the internet succeeded. The internet is forced by top-down control. I guarantee it will not succeed.
So what is the deadline? I mean, when does this thing come on?
When does it come on? We don't even have quantum computers yet.
Yeah.
So I'm talking about the long term in a future whereby, first of all, quantum computers are mass reproducible and they're good enough quality to do fault-tolerant computations. And we have some kind of networking capacity. It could be what they might have described, quantum satellite, or it could be smaller local US entities with fiber in the lab. It depends, but that will evolve over time. Certainly the network will come after the original computers, because the network demands the network operating system for computers. So this is very much in the post-quantum computing era rather than the pre-quantum computing.
Other than encryption, which everybody knows the use of quantum computer, which are the other big problems which could straight away solve, which we are not able to handle?
That's an ongoing question. Probably, I would say, at least based on what's known, and certainly lots of people believe that the most exciting applications for quantum computers haven't been discovered yet, which is probably true. But based on what's presently known, I'd say some form of application of either optimization problems, hard optimization problems that classical computers can't do easily, or quantum simulation problems like quantum chemistry, which are useful in, for example, drug design or genetics or anything at the molecular, biomolecular level where quantum mechanical effects are inherently at play and therefore very hard to classically simulate, have enormous importance in things like drug design.
But do you think this could make some qualitative changes than what are not achieved?
Yeah, it certainly could make qualitative changes. If we focus just as one example, say the drug design issue. Well, at the moment, what we do when we design a drug, we have to do a mass trial. We have to get millions of people involved. Half of them get placebo and half of them don't, and then we collect the data, and it takes decades to get FDA approval before the whole thing works. The medicine is changing. Now we're moving into the era of genetic medicine. By definition,